this is our analytical section for our free flight glider. Here at the top we have some basic force calculations just to figure out the force of lift and the force of drag. And if you look here on the right side in the workspace, your force of lift comes out to about 19 newtons, which is enough to carry 2 pounds. That's assuming a fairly slow takeoff speed of 15 meters per second. Now to getting into the structures, we're assuming we're using short-leaf pine with a modulus of elasticity of 12 gigapascals. The source is right here. It is from aimsweb.info. They had a nice little page on all the different woods. We used an 1/2 inch dowel in the center of the wing and a 1/4 inch dowel on both the leading edge and the trailing edge. In order to calculate the second moment of area, we assumed a perfectly circular cross section because the dowels are pretty close. So our force, we're using 8.896 newtons, that is 2 pounds. And then our C, our distance from the center, we're just assuming is half of. And then our shear force, we're going to assume is the entire force on the wing. So that'll be all 8.896 newtons. And our shear comes out to a nice little 7 kilopascals. So that's a very nice little value. And our cross-sectional area is calculated here for the 1/2 inch beam. Now we get into the Euler-Bernoulli to determine the displacement calculation. So I solve for the ratio of the force. You've got 3 dowels in the wing, so each one's going to take a certain amount of force, determined by the ratio of the second moment of areas. And then here we have the moment calculation. So that's just your force times your length. And then your actual bending stress is calculated here. That'll be your moment times your C divided by your second moment of area. Our stresses came out to be, here on the right side, about 20 megapascals and about 10 megapascals for the smaller dowels. And that is because what I'd solve for was the Euler-Bernoulli. When I equated the forces, I assumed that both of the beams will bend to the same displacement, and so the larger beam will end up taking a lot more force. And so calculating our maximum yield stress, maximum yield comes out here when you rearrange the Euler-Bernoulli. It comes out here to be, your maximum bending force is about 33 newtons for plastic deformation, and your maximum bending force comes out to about 17.7 newtons for recoverable elastic deformation. That is based on numbers I got that were yield stress of 41 megapascals and ultimate tensile strength of 78 megapascals.
When we first began our design, we decided to start with a basic airfoil shape, and in order to simplify the task a little bit, we found one that we thought was suitable that was already made. So when we go to this website, it's an airfoils tool website, it not only gives you a decent picture of the cross-section of the airfoil, but also gives you these data points down here. So basically what I did was once we specified which of these we would like to use based off of Reynolds numbers, etc., I was able to take this matrice and convert it into a MATLAB code. So here's the MATLAB code. As you can see, I've changed those data points into X coordinates and Y coordinates. And in order to make the graph proportional, we had to set each axis equal to each other, meaning that they had the similar spacing in between each number. So from 1 to 2 on both axes were the exact same distance. And then it was a matter of just plotting, and when you run the program, you're given a graph that looks like this. So this is now our personal image for what our airfoil will look like. And basically what I did is I saved this as a JPEG file, and I found that in SolidWorks you can open up a sketch and insert an image onto a sketch plane. So I inserted this image onto that sketch plane and then traced out a decent area around this airfoil that we want, trying to exclude any of the axes. And SolidWorks converted it into a SolidWorks sketch. From the sketch, I was able to adjust any lines that were not straight, any corners that were too sharp, etc., and also find a basic geometry so that we can do preliminary calculations. So, after I did that, I created our first iteration of the individual ribs that we were going to use on the first design, and our final design still incorporated the shape of airfoil and our rib design. However, it was not the original ones. The original ones were about 4 inches long from tip to tail and about a 1/4 inch tall and a 1/2 inch thick. So these were very small pieces, and we used a wooden dowel that went through the middle, and it was set with set screws from the top, and we had 5 on either side of our fuselage. So our fuselage was originally made out of a Pringles can with a Dr. Pepper nose, with the dowels a little bit closer to the front than the back to kind of help bring that the nose down while in flight. However, this design did not work out. It ended up actually breaking on one of our weighted experiments, so we found out that we needed to make it more robust in order to handle the requirements. So our secondary design incorporated the same airfoil using the same SolidWorks sketch, just scaled up by about a factor of 2, and had more dowels in the side than just the one, and we also just included a long dowel through the middle and some tail fins on the end to kind of help get it up and gliding. So here's our quad chart for the project. Our first section is the design inspiration. So our design came heavily from what is very common in aerospace, is a ribbed, thin-walled structure. So we ended up making dowels that would hold all of our individual ribs, which would define the shape of our wing, and we covered it in a thin layer of paper. This allows it to be very light but still have a large surface area. The next image you see is the airfoil that we started from, and it was the defining shape for our entire wing. So next we have the cost breakdown. So our total cost ended up being $10.21. This was mostly due to the dowels, specifically the 3/4 inch dowel was rather expensive, and Pringles can get up there as well. But everything else we were able to utilize things that we already owned, and that definitely helped us remain in budget. Next section is the prototypes and preliminary data. So this is a picture of the code we used when we were first thinking about designs, making sure it was feasible, and kind of just doing a sanity check. And the next image is our first prototype. This was our overall failed design due to it being too small and too fragile and not being able to lift the required weight. And finally, the challenges or design change suggestions. So first of all, the main challenge of this project was definitely the coronavirus kind of throwing a wrench in our plans. It made it a little bit difficult to finish the project as a group, but we did divide and conquer in a way that kept us all involved. The hardest part was the announcement came when it was already too late for us to switch to doing individual projects, so we decided to make do with what we could. Another issue we had was time coordination. So even before the coronavirus stuff kind of came and messed with everything, we all had very different schedules and very different times where people were free, so we had a little bit of trouble kind of scheduling to get that good line of communication. And so finally, our design change suggestions. I would definitely say if we were to do this again, we should probably eliminate the Pringles can altogether, because on such a small scale, it's a rather large, very not aerodynamic structure. And finally, maybe focus a little bit more on the angle of attack to get optimal gliding, and this would just optimize the distance that we would be able to throw.